the measure of success of the workshop is how many people are at the very last session after 4 very full days. So it's my pleasure to introduce Matt Valeriote from McMaster University, who will tell us about testing assignments to constraint satisfaction problems.
Thanks, Wolfgang. First, let me thank the organizers. It's been a wonderful conference, just really interesting talk. So thanks. Before I start, let me acknowledge two co-authors, Hubie Chen and Yuichi Yoshida. I take great comfort in having Hubie here, because if there's any hard questions asked, I'm going to rely on him to answer them. So where is Hubie? Okay, pay attention.
He started hiding already.
All right, so this is a talk on constraint satisfaction problem, and as all talks must start with, start with the definition. We've seen different ways to present this class of problems, and here's one way. We start with a relational structure. A finite relational structure has a finite set and a finite sequence of finitary relations. And we'll call it a template sometimes. And what's an instance of the constraint satisfaction problem over this template or the structure? It's a pair consisting of a set of variables, along with a bunch of constraints. And a constraint consists of a sequence of variables along with an attached relation from our structure. So we want to know whether there's a solution to this particular instance. And what is a solution? It's an assignment of values from our domain, from the set A, to the variables V, so that each of the constraints is satisfied. That is, for each constraint we have in our instance, when we assign our, look at the tuple that we get from this assignment, it lives in that corresponding relation. Okay? And again, this could also be presented as an instance could be a conjunction of atomic statements, and we want to know whether there's a satisfying assignment to it. All right. So, and again, every talk like this must talk about graph K colourability, because this is a very nice example of this. We look at the structure consisting of the numbers 1 through K and the inequality relation on this set. And an instance of graph K colourability, as you know, is just a graph, and the question, finite graph, and the question is, can we assign colors to the vertices so that no neighboring vertices will have the same color? And that amounts to just really an instance of there's a corresponding instance of the CSP of the structure, and the graph is K colorable if and only if this instance has a solution. Can we assign values 1 through K to the vertices so that pairwise we never get the same color for edge-related vertices? Right. So standard example. And yes, as we all know, when K is 2, this is this decision problem is in P, and otherwise it's an NP complete problem. And, well, have to also mention the classic decision problem here. Given a template and an instance of the CSP or this template, we want to know whether it has a solution, yes or no. This is an NP complete problem in general, but for certain templates, we actually get this problem lying in the class P. The Valeriote conjecture just states that really there are only two possibilities for a given template. Either this problem is easy or it's as hard as it can be. I'm not going to talk about this conjecture today. I want to talk about a different sort of problem. In Libor's talk, he talked mostly about the decision problem, but talked about other sort of directions one could go with this. And this is yet another application of the ideas that Libor talked about, and it has to do with property testing. So here's the setup. We've got a template A, and we've got an instance of CSP over this template. And I want to know whether a given function, an assignment, is a solution or not. How hard is that to decide? Well, it's not so hard, right? This problem class is an NP, so there is a fast way to certify that a given function is a solution, right? And in fact, depending on the computational model, you could even argue it's a linear time problem. So here, I'm assuming that I have random access to this function, or some oracle has the function in hand, and I can query the oracle, checking various values, and in sort of linear time and the number of constraints, I can get a decision out whether this is indeed a solution or not. Okay, it's not so important, it's just there's a fast way to check whether something is a solution or not. But fast is fast, and maybe the number of variables is extremely large, like billions and billions, and it'd be a real drag to actually have to check every single variable to see whether we have a solution or not. So even though it's a quickly testable kind of thing, it could take up a lot of resources to actually decide this. And maybe we want to make these decisions sort of quickly on the fly with using few resources. So if we relax our requirements to have sort of absolute certainty whether a given function in hand is a solution or not, we can test it instead. So here's what I mean by testing an assignment. I'll elaborate on this in a second. But what if I don't, again, want to know for sure whether I have in hand a solution or not? What if I just, say, want to test quickly, distinguish between satisfying assignments versus assignments that are really rather far away from any satisfying assignment? So that's what we're going to be considering. How can we come up with testing algorithms to deal with this sort of, address this sort of question? And under what circumstances will such a nice testing algorithm exist? Now, in general, really the best we could do would be essentially to read every single value here and then check whether it's a deciding assignment or not, a satisfying assignment or not in this way. But for some certain special templates, we can quickly test whether something's far from an assignment or is an assignment, as we'll see.
So are you willing to use randomness?
Yes, right. Yes, we're going to relax. We won't be certain what this thing will be. A probabilistic sort of algorithm that, with high probability, we'll be able to distinguish between a function that is satisfying versus far from being satisfying. So yeah, so I've used the word far a few times. I need to talk about some sort of metric here, and here's the one we'll use. So given a template A and an instance of CSP over A, I want to also have a weight function attached to the variables, essentially a probability distribution on it. And I went back and forth on whether I should include this or not. We could have just dealt with this sort of uniform weighting system here, but we're going to allow this arbitrary weighting system on function on our set of variables. So given two assignments from functions v to a, the distance between them, according to this weighting function, is just the weights of the variables where these two functions differ. It's kind of like a Hamming distance. If this were the uniform weight function, then that's pretty much what we're talking about here. So it's a measure between we can apply to two different functions from v to a. So now we introduce another parameter, epsilon. It's kind of our error tolerance here, a number between 0 and 1. And we'll say that f is epsilon far from satisfying the instance I if it's rather far away from any satisfying assignment. So it's not close in this sense to any satisfying assignment. Okay, so again, going back to our testing, we want to be able to distinguish with high probability functions that are satisfying versus those that are rather far away from any satisfying assignment. Well, so now we have to introduce what we mean by a tester. It's a probabilistic algorithm. So again, given a template, A, a relational structure, a tester for CSP A is an algorithm of following features. So on input, well, we're going to give it this epsilon, our error tolerance, an instance of CSP of A. And again, we might as well assume it's satisfiable, or else really there's nothing to test here. But let's not worry about that. We have this weight function attached to the instance. And again, there's this unknown assignment. We have query access to it. So there's some oracle that has this assignment, and we get to make queries of it. Again, we don't get to see the whole thing. Otherwise, we could just see ourselves whether it's a solution or not. And the output is either yes or no. If this assignment is a satisfying assignment, then our algorithm with high probability will output yes. Now, high here is 2/3. This is just some more or less arbitrary number that's used in these instances. We can amplify this, make this a bigger number if we want more certainty just by running this tester several times. But anyway, so we want our output to be yes if we do have in hand a satisfying assignment? Again, yes, with high probability. And no, whenever the function is rather far from any satisfying assignment. Yes?
So how is the weight function presented? Like if the weight function puts all of its weight on bit 4 million, you wouldn't find that unless it was presented in some...
Yeah, so let's see if I know the answer to that question. How is the weight function given to us?
Presumably the weight function is completely known.
Yeah, we do have the weight function sitting in front of us, so it's just this function here that we don't have access to. Right, so this is all given to us, the instance and a weight function for the variables, and we have query access to this function.
The weight function is as big as the assignment, right?
Yeah, it's as big as the instance too, right?
Right.
Yeah.
Do you mean can you sample according to the weight function?
Yes, we're going to do that, yeah.
So do you need to have a description of it? If you can sample from it, isn't
Oh, okay. These are questions I'm not sure I can answer. So it's... We're going to be sampling according to this weight function somehow. I'm not sure if that's standard, just build it into the oracle calls where you just make a call to the oracle and well, okay. Let's table that question. Yeah.
So basically, it's a sampleable distribution somehow.
That's right. Okay, so that's what we're after. We want to devise testers for constraint satisfaction problems over some fixed template A. And for the most part, the testers we'll be looking at are called one-sided. This does allow for us to miss certain functions that actually are satisfying assignments, but the ones we're dealing with are called one-sided. They're always correct for this. So if it is a satisfying assignment, then it will always give us the yes value out. Yeah, so as you can tell, perhaps this is a concept I'm not expert in. My contribution here is to sort of describe the templates which we do have nice testers. So I think I understand this concept well enough to at least be able to present a simple instance of what is meant by a tester. So suppose I have the property I want to test is whether a string of bits is constant 0. Okay, so imagine having a billion bits there, and you want to know whether it's constant 0. Well, you could check them all, but that could take a long time. Suppose I just want to check, the property is, yes, so suppose my epsilon is 0.1. And I want to sort of figure out with some high probability whether this bit sequence has more than 10% of 1. So say it's a billion, say a million bits here, and I want to know whether there's more than 100,000 ones in there or not. Well, the test could be just to randomly sample, I think 30 would do it, 30 random bits, and if I don't see a 1, then I will say yes, otherwise I'll say no. And you can do the calculation that independent of this 1 million or 1 billion, sampling 30 bits randomly with high probability you will see a 1 if more than 10% of the bits are 1. So that's the kind of tester we're talking about here. Good, so let's see. Right, so time could be an issue when you're doing these sorts of testing, but the resource that we really want to control is the number of queries we have to make. It could be that it's very expensive to query the oracle to get values out. Maybe the function stored some way a long way away, or maybe it's expensive to transmit this information. Maybe you don't want to transmit the whole solution because the lines are unsecure. So you want to minimize the number of values you actually have to check for various reasons. So this leads to the notion of a query complexity of a tester. And we'll say the query complexity of a tester is constant if, for fixed epsilon, no matter how many variables we're dealing with, we only need to make a constant number of queries to get our answer out. And we could relax that to have a sublinear complexity, where as a function of the number of variables in our instance, the number of queries we make is a sublinear function. And of course, the worst case, we're just going to be making a linear number of queries, linear in the number of variables. Of course, when we make epsilon smaller and smaller, we'll expect the number of queries to grow. But for a fixed epsilon, independent of the number of variables, we want to know whether we can get away with a constant number of queries or not. And so we'll call the query complexity of CSP of A to be constant, sublinear, linear if it has a tester with that particular query complexity. Yeah, again, in the worst case, it's always going to be linear, right? Because if you see the whole thing, then you can get your answer out. So here's the problem. Given a template, given a finite relational structure, how do you determine the query complexity of the constraint satisfaction problem over that template? And here's some background, some known results. For 2 coloring, yeah, it has constant query complexity. It's sort of like this example I just gave, that if you have a big graph, you just need to sample a small number of vertices to see whether the function you have in hand really is a 2-color, again, with high probability, or far away from one. Here's some non-constant query complexity templates. 2SAT, it's sublinear, and again, it's not constant. It has this as a lower bound for the query complexity. Even some nice CSPs have bad query complexity. So these are all have linear query complexity. This is a tractable instance of the CSP, but nevertheless, that's not going to help us with query complexity. Yoshida and Bhattacharya have solved this problem over the 2-element template, essentially doing a fish, lost track of the name. Who did the 2-element, the Boolean CSP? Sheffer type result for this problem over 2-element templates. And again, they got to sort of mirror this, a trichotomy over the 2-element templates. Yeah, and again, in some sense, the reason I'm involved in this is because this is essentially an algebraic sort of problem. That the observation of Yoshida is that the query complexity of CSP of A is determined by a particular algebra. This is the algebra of polymorphisms of the structure. And this is something that Libor talked about yesterday. So I won't go into this in too much detail, but a polymorphism, or we've been calling these symmetries, is a function on the domain of the template that preserves each of the relations in this sense. Another way to see this is these are functions that are homomorphisms from, for some k, A to the k, the structure into A. Again, there's symmetries of the template. So we gather together all these polymorphisms, we get an algebra. An algebra is a set with a bunch of operations. So this is the algebra of polymorphisms of the relational structure. And Yoshida observes that this complexity is totally determined by the properties of this algebra. So the game now is to uncover the algebraic properties that will, say, determine whether this has constant query complexity or not. So a couple of examples, more or less going over the list examples of polymorphisms that will come up. And I think Libor did mention some of these in his talk. A Maltsev operation is a function that satisfies these 2 equations. You've all seen algebras with this kind of operation. For G a group, the operation x times y inverse times z satisfies these equations. That's a Maltsev operation. Any algebra with an additive structure will have one of these things. A majority operation is another ternary operation that satisfies, well, these majority equations. An example of such an algebra with such a structure operation is a lattice. The operation x meet y join x meet z join y meet z is majority. Check that. And a generalization of this to what we call a near unanimity operation. This is a 3-ary near unanimity operation. This is a general version. These things sort of occur in nature, but they're maybe a little artificial. I mean, they do come up, and they're important to what I have to say. Right, so we'll come back to these. We'll see these a little later on. So templates that have or don't have these sorts of things, the template for graph 2 coloring has both Maltsev and majority polymorphisms. In fact, any structure whose relations are graphs of bijections will have both of these things. Okay? So they have a very rich set of symmetries. 3-lin, P, again we saw this yesterday, are just the structure or the p-element field whose that have binary and ternary relations that are essentially affine over the space. And because it supports an additive structure, we'll have a multi polymorphism, but you can check that it has no majority polymorphism. And the structure that codes up to SAT will have majority but no multisev. So there's various combinations possible here. And again, we'll see these a little later on when we state our theorem. And finally, again, Libor mentioned this, that the structure for 3-SAT has only trivial polymorphisms. All right. So here's a result that Yuichi presented at Fox last month. It does settle this problem. We know exactly under what circumstances the CSP of A will have a constant query tester. And in fact, it's exactly when it has these two nice symmetries, a majority and a multiset polymorphism. Yeah, this maybe isn't so critical, but these kinds of structures that have both operations have been well studied by algebraists, universal algebraists. These are called arithmetic, that the equational theory of such algebras are said to be arithmetic varieties. And example of such an algebra, if you take a finite product of finite fields, then such an algebra will have these two kinds of operations, so they will be arithmetic. And Pixley observed that, in fact, this one symmetry, this one polymorphism will give rise to both of these and vice versa. If you have both of these, you can get one of these. So just a more convenient way to capture, say, this property here, having a Pixley term. Good. So what I want to do is, in the last few minutes, is just talk about the proof at some level. Really want to illustrate how having these kinds of symmetries will allow us to devise a good tester. Of course, I don't have a whole lot of time, which is probably a good thing. So let's look at the negative side. If a template fails to have one or both of these kinds of symmetries, these polymorphisms, then why will there not be a good tester? Well, this is where some interesting algebra comes into the picture. If an algebra has a multiset operation but fails to have majority, then one can capture that in more structural ways. It turns out that this will happen if and only if the structure in some sense interprets a module or some sort of additive structure. And in the way that Libor was talking about yesterday, so really, if our template fails to have both of these polymorphisms, then it can PP interpret modules. And since testability over the query complexity of testing over, say, an additive structure like a module is going to be linear, that carries over to the template A. So on the negative side, we find bad interpretable structures, and that lifts to bad query complexity for the given template. There's another reason for there to not have constant query complexity, and that is if we fail to have a multiset operation, then we can PP interpret a structure that has a single binary reflexive but not symmetric operation or relation. And again, we can use that. That's going to have bad query complexity, and that lifts up to the given template. Yeah, we modify an argument from Fisher for 2-SAT to get this lower bound for the query complexity of CSPA in this case here. So there's a quick sketch of the situation when we don't have both of these nice symmetries. On the other side, we're going to use these polymorphisms to really rewrite our instance. It might take some time, but not so much, both for me and for the pre-processing. You imagine starting with some random instance with huge arity relations and lots of variables. What we can do is pre-process things to convert this into a much better instance to deal with that has the same set of solutions. What we get is an instance where all the constraints are binary. So every variable, we have this domain, this algebraic structure A sub x, A sub y, and all the constraints between variables will be binary. And between any two variables, there will be a constraint. So we have this nice complete graph constraint network, if you like. And we use the majority polymorphism to reduce high arity constraints down to binary. We also establish some sort of local consistency so that given any two edge-related elements in these two domains, and given the third here, there will be a way to complete this in this way. So we can use a majority polymorphism to really transfer the original problem into a much nicer one. The way we use the multiset polymorphism is as follows. So given to these domains, say over the variable x and the variable y, what follows from this multiset polymorphism is that the constraint relation Rxy is very much like a function, that there are compatible equivalence relations on both domains such that R is essentially just it's a function mapping classes to classes. So the multiset polymorphism gives us a really nice picture of what these constraint relations are. The majority allows us to really reduce things down to this situation. And while we have to do a fair amount of more pre-processing using these two constraint relations, in the end, well, we get to the point where it becomes more or less transparent. So the testing amounts to sort of testing in the end. So we'll transform to the point where we get lots of isomorphisms between domains. And so the testing will be just to select a bunch of points and seeing whether the function f respects these isomorphisms. Yeah, I don't think you can say a whole lot more given the time. So let me just skip over the sequence of reductions that allows us to transform this into essentially a transparent sort of instance. Yeah, so I just in passing mentioned those things, but in the end, we get the following kind of result, that if our template has these two nice polymorphisms, then the query complexity will be constant and on the order of this. So of course, as epsilon gets smaller, we'll need to sample more points, and it grows in this way. Just to wrap up then, it's a one-sided error tester as well. We could extend this to the situation where we allow existential quantifiers. This is a richer class of problems to consider. And again, in the same paper, we get a trichotomy that, again, sort of looks like the result I just dealt with. If we have both of these nice polymorphisms, there's a constant query tester for this larger class of problems. And otherwise, it's not constant. We have this middle ground where there's a sublinear tester, and that's when we have one of these near unanimity polymorphisms. And otherwise, we get to the linear case.
What is exist CSPA?
So it's where we allow some. It's a primitive positive formula. So we have some existential. We have some free variables, and then some quantified variables, and then a conjunction involving both the x's and y's. We want to know. Yeah. So 5x is a PP formula, and we want to know. We're testing whether an assignment to the variables x is a solution or not, or far from one. So yeah, we allow, whereas in CSP we don't allow quantifiers here. It's just
you take projections. Okay.
That's right. So this is a richer class of problems, and we're somehow our methods. We have in interpretation we're using lots of existential quantification. So we can get this out, and to end the problem is. Can we get this trichotomy just for the usual old CSP? And that's an open question. We have some interesting ideas on that, but just haven't panned out yet. So that's it. Thanks for your attention.
Questions for Matt?
Today.
What happens if you don't allow those weights?
Just straight with uniform? Well, I think we internally will need to deal with them because one of in our reductions, we have to split variables into two. And so we have to sort of split the weight of that one variable into two equal parts. So I think internally we have to sort of track these weights.
No, but it may make proving hardness more difficult. So don't you get more, say, these easy cases?
I see. So so we're simplifying the class. We just allow the uniform weights. Is that?
Yeah.
I'm not sure. That may be a good way to resolve this thing, at least in part. Yeah. Thank you.
Other questions? Yeah.
Is there a relationship between this epsilon testing and probabilistically checkable proofs and hardness of approximations?
I have no. Hubie, help me out here. I'm not really. So yeah, I don't know anything about that, unfortunately. Is there? Oh, please.
I asked if there was a relationship between epsilon testing and probabilistically checkable proofs.
A lot of this framework of testing was developed in order to understand what was going on there.
with a capital P.
PCPs.
But maybe, like, on a high level, you could say that in PCPs, you want to, I mean, the PCPs are formatted in some nice way to allow for a small number of queries. But here, we're not really formatting, you just have a plain assignment, right? So that's maybe a high-level difference.
Okay.
But in general, that led to the question, you know, when can we test? What types of things are testable?
So here's an example of that, right?
So same people working on both problems. This is the main relationship.
Not me.
No, I mean originally.
Yeah.
Right, well, thank you very much.